The sun might look calm and unchanging from our perspective, but in reality, it's a colossal nuclear furnace in constant motion. Its surface boils with activity, unleashing violent solar storms and streams of radiation racing toward Earth. Dark sunspots drift across its fiery face, while immense magnetic fields ripple through the solar system. Only recently have we begun to grasp just how deeply the sun influences our planet. It can create chaos on Earth, but with rising global temperatures, could it also be part of our salvation? This blazing giant, made entirely of superheated gas, could swallow more than 1 million Earths within its bulk. It fuels every form of life on our planet by providing a steady flow of energy. For over 4.5 billion years, it has sustained oceans, forests, and all living creatures. Humanity has thrived during a period of relatively stable warmth since the last great ice age, but scientists now realize this balance may not last forever. The sun's relationship with Earth is far more complex than once thought. Explosive. Clouds of plasma can burst from its surface, striking our outer atmosphere and sometimes disrupting satellites or even power grids. Its vast magnetic field constantly interacts with Earth's, a tug-of-war playing out every minute. These magnetic surges rise from deep within the sun, creating sunspots, dark patches that reveal cycles of intense activity. This cycle rises and falls roughly every 11 years, swinging between solar minimum, when few spots appear, and solar maximum, when the surface is crowded with them. But what does this mean for us, 93 million miles away? More than we ever imagined. Historical evidence suggests that variations in solar activity may have shaped Earth's climate in ways once overlooked. Understanding this link has become urgent, as it could prepare humanity for the challenges to come. Modern space observatories give us an unparalleled window into solar behavior. NASA's twin stereo spacecraft, launched in 2006, were designed to capture three-dimensional views of eruptions and storms that ripple across the solar system. By positioning the two satellites at different angles, scientists can now measure the speed and direction of massive plasma blasts far more accurately. These eruptions, containing billions of tons of superheated gas, can reach Earth in as little as 12 hours, disturbing our atmosphere, disabling satellites, and creating spectacular auroras at the poles. Solar storms are essentially giant electrical tempests. Like lightning, they can short-circuit technology, disrupt GPS, and even endanger astronauts. But thanks to three-dimensional imaging, scientists can better predict their timing and intensity. Sunspots, the dark blotches on the sun's surface, are at the heart of this drama. Once a mystery to early astronomers, they are now understood to be linked to the sun's nuclear fusion process. They arise when turbulent flows of hot gas twist magnetic fields into tangled loops. These loops can break, reconnect, and unleash powerful bursts of radiation, sometimes in the form of X-rays or gamma rays invisible to the naked eye. A single sunspot can dwarf Earth, spanning an area the size of Africa or larger. Though they look dark compared to their surroundings, in truth each one shines brighter than a full moon. They are windows into the sun's hidden magnetic forces, and potentially into much larger cycles that affect Earth itself. In fact, centuries of records suggest that prolonged declines in sunspot activity have coincided with episodes of global cooling. During the Little Ice Age, from the 14th to the 19th century, unusually cold winters gripped Europe and North America. Rivers froze, crops failed, and societies struggled to adapt. Astronomers later discovered that this period matched a time of exceptionally low solar activity, known as the Maunder minimum. Today, scientists are uncovering evidence that links sunspot cycles, cosmic rays, and long-term climate shifts. When the sun's magnetic field weakens, more cosmic rays from distant stars reach Earth's atmosphere, altering isotopes preserved in tree rings and ice cores. These records act like a time machine, letting us trace solar behavior back thousands of years. The story they reveal is one of constant change, where even slight variations in the sun's activity can leave a mark on Earth's climate. Cosmics. Rays born from colossal explosions like supernovae race through the universe at nearly the speed of light. Earth is constantly bombarded by them, and over time they leave hidden fingerprints in tree rings and layers of ancient ice. When these high-energy particles collide with our atmosphere, they generate isotopes such as carbon-14 and beryllium-10, natural markers that allow scientists to trace solar activity stretching back thousands of years. This discovery revealed a fascinating pattern. When the sun's magnetic field weakens, fewer cosmic rays are deflected, leading to higher levels of isotopes recorded in nature's archives. During periods of strong solar activity, the field stretches billions of miles into space, shielding Earth more effectively and leaving fewer isotopic traces. In other words, tree rings and ice cores act like a cosmic diary, chronicling the sun's hidden rhythms across millennia. To demonstrate how magnetic fields shape these particles, researchers at advanced physics laboratories use beams of electrons as stand-ins for cosmic rays. As current flows through magnetic coils, the electron stream bends and shifts, just as cosmic rays are deflected by the sun's invisible shield. This simple experiment makes clear how deeply solar magnetism influences the radiation that reaches Earth. The connection between sunspot cycles and cosmic ray levels also sheds light on past climate changes. During the Maunder minimum, for example, isotopic evidence shows a spike in cosmic rays, aligning with a dramatic drop in solar activity. The sun's surface was nearly spotless for decades, while Earth entered one of its coldest intervals in recent history. Such evidence suggests that solar variability, though not the sole driver, plays a significant role in shaping long-term climate patterns. Some scientists now warn that we could face another sharp decline in sunspot activity in the near future. If so, the sun might enter a prolonged quiet phase, altering the balance of cosmic rays that reach Earth and potentially influencing our climate once again. Predicting this is challenging, but by monitoring the sun's magnetic fields at the poles, researchers can estimate the strength of upcoming solar cycles. The greater the magnetic flux carried toward the poles, the stronger the next cycle of sunspots is likely to be. Yet even this method has its limits, and the possibility remains that one day a solar cycle may simply fail to appear. Meanwhile, Earth's own orbit introduces another layer of complexity. Roughly every 100,000 years, slight variations in the shape of our orbit alter how much solar radiation we receive. When the orbit becomes more elliptical, differences in sunlight between the closest and farthest points grow dramatically, helping to trigger major ice ages. At present, our orbit is relatively stable, producing only a mild variation, which is why the climate has remained temperate since the last glacial period. But history tells us this balance will not last forever. The sun, with its magnetic storms, quiet spells and long-term cycles, remains one of the most powerful forces shaping our planet's destiny. By uncovering its hidden patterns through satellites, isotopes, and centuries of records, we are only beginning to understand how deeply it ties Earth's fate to the rhythms of the cosmos.